How did you do? So let's check how many people got through all of the required exercises in the technical. There was one at the end that was hard. How many people got through a substantial part? Okay, substantial number, but not everybody. So, I think what I'm going to do is go on and show you something about logic, but not too much, and then take a nice long break and give you more of a chance to get started working on things, or continue working on things. So, the next chapter then that we have to talk about is called logic, and surprisingly enough, it's about how to do logic in talk. Of course, we've been doing logic already, but we haven't seen some standard vanilla logical connectives like and or and not, and you may be wondering where they are. So let's talk about them. So what we've seen so far, just to review, we've seen the fundamental propositions that we've seen have been equality propositions. This thing is equal to that thing. And then on top of that, we've added implications and quantified propositions. And then we've also, of course, seen proofs. So kind of coming along with each of these styles of proposition were some tactics that allowed us to manipulate goal states involving those propositional elements. So as we go along in this chapter, we're going to see several more varieties of propositions and accompanying proof styles. Okay, so the first thing to recognize is that in Coq, of course, everything is typed, so propositions are typed. What is the type of propositions? It's called prop, surprisingly. And it looks like this. So the proposition, or the expression 3 equals 3 is well typed, and its type is prop. That is, in Coq's world, it lives in the logical side, and it is a proposition. What is a proposition? It's a logical claim that may be either provable or not provable. And what is a proof? It's evidence for a claim. So propositions can be simple, like 3 equals 3. They can be more complicated, like for all, blah, blah. But the type of each of those logical claims is just prop. It's important to note that being a proposition and being a provable proposition are two very different things. So 2 equals 2 is a proposition. For all n equals 2 is a proposition. And 3 equals 4 is a proposition. So these are all propositions. They're perfectly good propositions. They differ in their degree of provability, but they are all valid propositions. And of course, that's important because we need to be able to write down both true and false propositions so that we can prove the true ones. Okay, so far we've seen propositions basically in one place, which is after the colon in an example or theorem. And what I want to begin by showing you is that there are some other places they can appear. For example, we can make a definition of an identifier of type prop. So we can say definition plus fact equals 2 plus 2 equals 4. And then later on, we can use, instead of writing out the proposition 2 plus 2 equals 4, we can use the name of the previously defined propositional variable. Also, all of that is kind of what you might expect. This gets a little more interesting. We can write parameterized propositions. That is, we can write functions from, say, numbers to propositions. So here is a function that, given a number n, yields the proposition n equals 3. So for some n's, it's going to yield a true proposition. For some other n's, it's going to yield a false proposition. But for every n, it will yield some proposition. So what is its type? Of course, its type is that arrow prop. Functions that return propositions are a very useful kind of thing, and they're so often used that we give them a special name. We call them properties. So a function from numbers to prop is a property of numbers. Why? Well, for each number, it picks out a proposition. Some of those propositions are provable, and some are not. And we say that the numbers for which the proposition that results when you apply the function is provable are the numbers for which that property holds. Okay, so a function from numbers to propositions picks out a set of numbers, namely the ones for which the resulting proposition is provable. And so that function itself can be regarded as a property of numbers or a set of numbers, speaking formally.
Provable means it's true, but it can be true, not untrue.
Indeed. So I knew I was going to have to talk about this at some point. I keep switching back and forth between the word true and the word provable. And in Coq, in every interesting logic, those are different concepts. In Coq, they're particularly different concepts because Coq is a constructive logic. So in classical logic, those of you that have taken logic courses will know that in every interesting kind of logic, there are propositions that are true in the sense that if you look at the intended model of the logic, the proposition holds in that model. And yet, you can't prove it because every interesting logic is incomplete. We know that from Gödel. So even in classical logics, the notions of truth and provability are not quite the same thing. Every provable proposition is true, but not every true proposition is provable. In constructive logics, the gap is even a little bit bigger because we disallow, we tie one hand behind our back and choose not to use certain axioms like the law of the excluded middle or double negation or there's a list of other things that in classical logic we employ freely, and in a constructive logic like Coq, we choose not to use. So this gives rise to a set of propositions that are true and classically provable and not constructively provable. What practical impact does all of this have? The distinction between true and provable is important. The distinction between constructively, classically is not worth worrying about too much for two reasons. One is that there aren't really that many interesting things that are provable classically but not constructively if you're willing to work a little harder. And second, if you need classical reasoning in Coq, you can just add an axiom. So it is perfectly reasonable and done to extend Coq's built-in base logic with extra non-constructive axioms that make the logic more powerful and that are known to be consistent. What do I mean by the word constructive? I mean basically that proofs are executable. So a proof of a proposition is a method for doing the thing that the proposition describes. And there's a long story about why Coq is that way that we don't have time for, but consistent with the very beautiful pun that Koch makes between functional programming and logical reasoning, that it would make that choice. Okay. So here is, coming back to the slide, here's a property, here is a polymorphic property, a property that, that could hold of any of elements x and y drawn from any type A. It says, sorry, what am I saying? No, it's a property of functions f of type A or B, where you get to choose A and B, that says f is injective if for every x and y in A, if fx equal fy, then x equal y. So this is the familiar injectivity property expressed in Koch. And of course we can prove it, and the proof involves inversion.
Well, first of all, the proof you have there is for one instance of it for successor.
Excuse me, thank you. Right, and yeah, what I said a second ago that we can prove injectivity would not make sense. We prove that a particular function is injective.
Okay. The other point is, this sounds a lot to me like something that Holzberg called axiom schema. An axiom schema, a property does. Except that an axiom schema is that you're assuming that it's always true that we put it.
Right. Yeah, so by the word schema, people usually mean some kind of polymorphism. But this is not an axiom. This is not something I'm assuming. It's something I'm defining that that it's a property of functions that holds for some functions and doesn't hold for other functions.
I know that this works whether it's a constructor or something.
And this will work, this definition works both for constructors like S and for functions. For example, we could say injective pred, where pred is the predecessor function, and that would of course give us a not provable proposition. Everybody's favorite polymorphic property is equality. Excuse me, I should not call it a property. Property is really is for unary functions returning proposition. For binary functions returning propositions, we would say relation. So equality is everybody's favorite relation. And in Koch, the expression n equals m that we've encountered many times before is actually syntactic sugar as a notation for EQ in m, where EQ is a lower level thing of this type for all A or prop. Sorry? What scope is it associated with? I have no idea. Some very global one. Okay, let's do a few in-class exercises together. So think to yourself and choose one of the following alternatives. What is the type of that expression based on what we've said? I'll give you about 4 more seconds. And then tell you that the answer is prop. So this is a prop. Plain old prop, not parameterized. What about this one? So this is also prop. This is a plain old logical plane. It's quantified, it has a quantifier in the front, but its type is still prop. It's a logical proposition. And this one? Same, also prop. This one happens to not be provable. previous one was. What about this one? This is not double typed. Because it's for all n some number. This doesn't make sense. It's a logical beginning and a computational end. And this stuff put together. How about this one? This is a function from numbers to numbers, so it's choice 3. Yep. Every natural number does have a predecessor. Predecessor of 0 is 0. And what about this one? Choice 2. This is a nat arrow prop function. Sorry? Process elimination, yeah. And what about this? Which of these things is not a proposition? Three. 3 is a plain old Boolean. Okay. Let's talk about and. So and in Coq is written with forward slash backslash, or when it's ASCII-fied, it looks like that. And is a function, if you want, that takes two propositions and yields a proposition. And since I'm now introducing a new kind of logical thing, I should also introduce a way of proving things with it. And that way of proving things is called split. So let me show you that. Font size readable? No? Let's do that. The next size up does that. Well, that's okay. We'll make it do. What side are we talking about? The left side. Oh yeah, I know that's not reasonable. Okay. No.
Toggle truncate lines.
Oh, that's true.
You can just involve show up, right?
You can go control X, curly brace, and expand one.
Well, that's really brace. Yes. Yeah, that's really brace.
The second part of the verse.
Oh, yeah.
You can go
Quite a
once
few.
you can go control X and then press Z repeatedly and then chaos.
Oh, there we go. Okay, this is good enough. So let's do this proof. So, how shall we begin? I don't know. It doesn't look like any of the tactics that we know so far apply. Oh, but remember we said split. Let's see what happens if we do split. So we had a conjunctive goal. We had to prove two things. We had to prove the conjunction of two things. Split says make two sub-goals, one for the first one for the second one. Now, well, each of these is easy. That's just going to be reflexivity in both cases. Okay. Conversely, suppose that we know two things and we want to get a conjunction out of it. Well, here's a little theorem that says if A and if B, then A and B. And this theorem is provable. I'm not going to bother stepping through the proof, but it's a pretty simple proof. No, actually, let me do bother. Okay, so we have to prove this long thing. Of course, intros makes it shorter. Now we have to prove A and B, and in the hypotheses we have an A and we have a B. So to prove a conjunction, we should split. Now we have to prove A. Oh, but that's easy. Apply HA. And we have to prove B, but that's also easy. Now, it's worth mentioning just to illustrate that there are many ways of doing the same thing, that instead of split, once we've proved and intro, we can use it basically instead of split. Why? Because and intro is a conditional fact. It says you can prove A and B if you can prove A and you can prove B. So if we have a conjunctive goal and we say apply and intro, it is going to generate unification variables for A and B. Then it's going to lay the conclusion of this unification variable and other unification variable on top of the goal. The two sides of the conjunctive goal are going to get unified with those two variables, and then we're going to generate subgoals for each of the hypotheses of this statement, one for A and one for B. Okay, so apply and intro is going to work just the same as split. All right. Now, so this was illustrating how to prove conjunctive statements using split or and intro if you want. What about if we're given a conjunctive statement, how do we use it to prove other things? Here's an example of that. Suppose we want to prove that if n equals 0 and n equals 0, then their sum is 0. Let's begin with an intros. And now we have this conjunctive hypothesis C. So how could we get some juice out of that hypothesis using one of the tactics that we know? Split goes the wrong way. Destruct. Or indeed inversion would also work. Destruct and inversion have a significant overlap. Destruct is lower level, inversion is fancier, it does more things. This is a case where you could use both. So what does destruct mean? It means kind of case analyze how C came about. How could C come about? Well, only by combining two previously known things into this conjunction. So if we say destruct C, we get two separate hypotheses with names that were made up by Koch, because I didn't bother to say as. And now we can rewrite using those hypotheses and prove the result by reflexivity. All right. Now, this slide says as usual, but I haven't actually told you yet. Just as a convenience, we can do an intros and a destruct at the same time. And the syntax for that is, instead of writing intros NMH and then destruct H, well, we would write destruct H as, and then give some pattern. We can just give the pattern in place of H. So what does the pattern do? It tells you what names to give to the parts of H that are going to get dumped into the hypotheses. Here there's only going to be one sub-goal, so we don't need any vertical bar in the as pattern. We just need, it's going to generate two things in the hypotheses, so we give them both names. All right. One kind of stylistic thing is, you might wonder, why did we bother in writing this lemma? Why did we bother putting a conjunction between the two hypotheses? Why didn't we just write n equals 0 and arrow n equals 0, arrow n plus n equals 0? The answer is, in this example, we could perfectly well have done it that way as well. In more complicated examples, it's not necessarily so easy, and you may, in the middle of a proof, find yourself with a conjunctive hypothesis that you need to be able to break apart. Okay. Just like pairs, it's frequent that we're given a conjunction and we just need one part of it. So we can define projections out of a conjunction. They are lemmas, they're propositions that go from, that say P and Q implies P, or P and Q implies Q. So these are things that you can apply as needed if you just want to quickly extract one part of a conjunction without bothering to do destruct. And they're easy to prove. And then two more, again, easy to prove facts about conjunction are that it is commutative and associative. And these little theorems are often useful when you're manipulating a complex proposition and you just need to get things into the right order to apply some other known fact.
Please, if I'm looking for the search for work with notations.
Search does work with notations. Yeah, so in Coq there are various ways of searching for previously defined things, in case you forget that this is called and commute and assoc. There are various ways of searching for, tell me everything you know involving and. Okay, and then Perry just implicitly referred to the fact that the and symbol is, of course, notation for something that we can write in letters and numbers. In particular, it's called A and D. So A and D is a function taking two propositions and returning a proposition. Okay, so much for conjunction. Please.
Is there a technical reason we didn't define and in the inductive machinery?
So could we define and using the inductive machinery? Why am I talking about it as if it were built in? We absolutely can define it using the inductive machinery, and that is the way it's defined in the standard library. So and is not built in any more than pairs are built in.
Right, so the instruction will always be on a and intro.
Say that again?
So the introduction will be definition and intro you have.
Right. So if we defined it inductively, the introduction form would be the constructor, and the elimination form would be destructing the constructor. And in Coq is not defined as a special form of existential quantification. They're defined as separate things. They're defined in the library as separate things. Prof is like stuffing classical logic. Well, it's like stuffing classical logic, but it's constructed. purposes of this chapter, I want to ignore the previous 2 minutes and pretend that and or and things like that are primitives. They aren't, they're definable. But I think it's easier for the moment when you're just getting used to them to treat them as atomic things and not worry about what's going on underneath, and just learn to manipulate them. And then later on, it's interesting to see, oh, you actually don't need them as primitives, you can define them in terms of yet more primitive stuff. But that's more of a kind of intellectual exercise about how cool the core logic is, rather than what you need to know to get work done, which is what we're concentrating on. Just a question? Okay, so let's talk about OR. So OR, again, is a function of type prop arrow, prop arrow, prop. It's a binary operator on propositions. And so here it's a little bit I'll talk about it in the other order. To use a disjunctive hypothesis, we need case analysis. So let's see, shall we actually look at it in the IDE? No, let's not bother. So if we do this intros, notice that in the intros, there's an as pattern with a vertical bar in it. The vertical bar in it means destruct. The whole as pattern means destruct. The vertical bar means there are multiple constructors, so we're going to generate multiple subgoals. So this intros with automatic destruct is going to generate us 2 subgoals. In one subgoal, the hypothesis is going to be n equals 0. And in the other subgoal, the hypothesis is going to be m equals 0. And our job is going to be, in each of those subgoal states, to reason until the subgoal is finished and we've discharged it. And if we can do that, then the whole statement is provable from a disjunctive hypothesis. Right, so once again, if you know P or Q and you're trying to show R, it suffices to show that from P we can prove R and from Q we can prove R. Because now we know that whichever of P and Q was true, we can derive R. Okay, and then conversely, we need a way of showing a disjunction. How would you show a disjunction? Well, one way of showing P or Q is to show P, and another way is to show Q. And in a constructive logic, those are the only 2 ways. In a classical logic, there are certain cases like if your disjunction has the form P or not P, then it's axiomatically true. And that is a perfect example of something that is constructively, a reasoning step that's constructively valid, but that's classically valid, but not constructively. Okay, so in a constructive logic, sort of the whole point of a constructive logic is knowing P or Q means either knowing P or knowing Q. That's what makes it constructive. Where knowing means having a procedure for P or Q. So to have a procedure for P or Q, you have to have a procedure for one or the other. Okay, so let's look at OR control. There's a little lemma. Suppose we want to show A implies A or B. Well, this is just the reasoning principle that we've been talking about. So after some intros, we're given a context in which we have an A. We want an A or B conclusion. And the tactic that does that is called left. So left says, I have a disjunctive conclusion. I am going to choose to work on, I'm going to choose to show you that the left-hand side is the one that holds. it's fine if both hold, but I'm going to make a choice that I'm going to give you evidence for the left-hand one. So if I do that, the goal changes, we throw away the B, the goal changes to now you just have to show A, which of course in this case is easy. Okay, so much for disjunction. I'm talking through this kind of fast in the interest of giving you a good long break to work on things. But please slow me down with questions if you have. So, we have conjunction, disjunction, we better have negation. Negation in Coq is a little, I find, a little harder to understand than conjunction and disjunction. Negation in Coq is defined to be, so not P is defined to be P implies false. Where false is a particular not provable proposition that's defined in the library. So, the not operator, which is what the symbol means, and by the way, the ASCII symbol for that is the tilde. So the not operator is a unary function from propositions to propositions, and it just means P implies false. So to work with negation propositions, I guess I had to finish the proof before. I wasn't happy with spelling the module. There we go. Okay, so suppose we want to show that for any P, false implies P. This is a very familiar and long discussed reasoning principle. In fact, it's so familiar and long discussed that its name is Latin. Ex falso quodlibet means from false follows anything you want. So let's prove it. So obviously we want intros. And now we have to show false implies P. Oh, how's that going to work? Well, let's do another intros. Okay? Now I have a hypothesis of false. And at this point, just like other contradictory hypotheses or nonsensical hypotheses that we've seen, I can do, I think destruct and inversion both work. Let's find out. Yes. So I can do destruct C, which says to Coq, please figure out all of the possible ways that false could have been proved and give me a subgoal for each one. Well, there are none because false is not provable. So we get 0 subgoals, and that proves whatever we want. Okay, let's see some more examples with false. So we can of course prove that it's not the case that 0 equals 1. Let's see that proof. By the way, not something equals something is such a common thing that, that we have notation for it. So not 0 equals 1 is actually displayed as, and you can type it in as 0 not equals 1. Okay, so how are we going to prove that? Well, just looking at this is why reasoning with negation is a little bit funny. Just looking at the conclusion, it might not be obvious what to do, but there's a not hiding in the notation, and not is a defined concept. It means false implies. So if we if we unfold, I'll try this to be more clear. No, sorry. Rewind that. Look at contra. It says 0 equals 1. Well, that is patently wrong. It's so patently wrong that it's wrong simply by virtue of the principle of disjointness that we saw in the morning, where so 0 is the constructor O, 1 is S applied to something. They can never be equal. So if we invert or destruct that hypothesis, we get any goal we want. Okay. Now, it takes a little practice to get used to working with negation, because you sometimes have to do what I was trying to do a second ago, unfold the definition of not, and then maybe get something into the context, or maybe destruct something. So I found when I was learning talk that manipulating propositions involving not took a little practice. There are plenty of exercises in this section to give you practice. So I recommend just working a few of them until it starts to feel natural, and then jumping to the next. Let's do just one together. How about this one? Let's prove that P and not P implies any Q you want. So we certainly need to begin with an intros. P, Q, and we have a hypothesis H. Now, how can we make progress? Well, we have a structured thing as a hypothesis. We have H. That's a compound thing. So I would make progress by destructing H. So destructing H gives us names for its parts. One part is P, and one part is not P. All right. So, but was that progress? Or am I stuck? Yeah. What if we unfold not? That's a thought. Replace it by its definition. Unfold not in H0. Oh. Well, now we've got a hypothesis that says P implies false, and another hypothesis that says P. So if I do apply, this is going to be an apply in, isn't it? It's going to be apply H0 in H. And now, voila, H changes to false. And now I can do destruct H. And I'm done. Okay? So this is the flavor of working with negation. If you get confused and there's a negation any place around, try unfolding not and see if it helps. Here's a little trick. If you're trying to prove a goal that looks nonsensical, it often helps to change the goal to be literally false. And you can do that by using X false equivalent, which, remember, allows you, says from false you can prove anything. So if we apply X false equivalent to any goal, that just replaces the goal by false, because that's the hypothesis of X false equivalent.
It seems like not is not as often unfolded as certain other things. Like sometimes when we do simple, it will unfold automatically, but not seems to be a bit more conservative with that. Is there a reason for that?
I find not a little confusing when it gets unfolded. prefer just to see, not P rather than thinking about if I had P, then I would have false, and what does that mean? So I think it's conceptually convenient to leave it atomic, except when occasionally you get confused and have to open it up. But what happens is that people define higher level lemmas in terms of not. And then, if you have a not hypothesis and a lemma that wants a not, then you just supply it directly, you don't need to build anything. All right, and by the way, I said we can apply X false equivalent bet to any nonsensical looking conclusion to replace it by false, which sometimes kind of simplifies things. There is actually a tactic built in called X falso that does the same thing. Okay, I'm going to skip over these because I only have a couple of things that I have to say before sending you off on your own. So we've seen the proposition false. So false is a constant proposition. It comes from the Coq library. And it isn't provable. One might expect that there would be another proposition, true, that is provable. And there is. So there's a proposition called true. And in the standard library, there is a constant I, whose type is true. That is, if you remember back to when we defined lemmas, the thing on the right of the colon is the proposition. The thing on the left is its name. Oh, wait a minute, but that looks like a typing claim. Isn't this saying that I is something that has type true? Well, yes. So that's a pun that Coq makes. This is coming back to Coq's claiming nature. A logical proposition has type prop. A logical proposition is the type of its proofs. If that's confusing, set it aside. Even if it isn't confusing, set it aside. And let's go back to this. So in the standard library, there is a predefined proposition true, and there's a proof of it called I. That's all you really need to know. False is used all over the place because negation is a common style of reasoning, common primitive for stating things and proving them. True is much less used because it isn't very useful, because given a hypothesis of true, what can you do with that? Well, of course it's provable, but the proof is not informative. It's just this I thing that you can't get any work out of. So true is not used as much as false, but it is used, and we will see some examples in the next lecture of where it can be quite useful. Where it's useful is when you're programming with propositions, which we will come back to. For now, let's set it aside. Okay, we need if and only if, of course. We have implication in one direction. If and only if is just implication in two directions. So P, if and only if Q, is P implies Q and Q implies P. There is a little bit of specialness about if and only if. Namely, an if and only if proposition is quite a bit like an equality, in the sense that, so suppose you have an equality hypothesis, and then, so suppose you have n equals m, and then you have some long formula involving n and m. You can rewrite that formula replacing n by m or vice versa. It's quite similar with if and only if. Suppose we have a hypothesis, P if and only if Q, and then some long formula involving P and Q. Well, if P if and only if Q is an assumption, then we can replace some of those P's by Q in exactly the same way as we did with equality reasoning. In other words, it makes sense to think of rewriting with if and only if assumptions in the same way that we rewrite with equality assumptions. And indeed, Coq provides a notion of so-called setoid rewriting that extends things like rewrite to if and only if and similar things. Let's not go into too much detail about that. There's a whole kind of pile of mechanism there that we don't really need to talk about. I just wanted to show you the tip of the iceberg, which is, if you have an if and only if proposition, you can rewrite using it.
Even though it's not associated, syntax. Well, I just noted that the introduction of the notation didn't allow you to write
Oh, I see. Yes, we don't have notation for P if and only if Q if and only if R. Just the binary thing. I suppose if you want, you could probably coax Coq's notation mechanism into doing the entering one. But I don't think it would be useful too often. Right. Here's one more nice thing, which is if you have an if and only if, and you apply it, the apply tactic works not only with P implies Q, it will also work with P if and only if Q. If you have a goal that looks like P, and you apply a hypothesis that looks like whose conclusion looks like P if and only if Q, it will change the goal to Q. And if the goal looks like Q, it will change it to P. So it tries both directions. That can often be nice. Okay. Existential quantification, I think this is the last. We have universal quantification for all. Of course, sometimes we need existential quantification for stating logical properties. For example, here is the property that says 4 is even. Reading it more carefully, it says there exists a number such that 4 equals that number added to itself. So this is the claim that 4 is even. And this funny looking proof, let me show it to you in ASCII. Too many things. All right, no. It's because of the ripping out things that I did when I was making the lecture shorter than the whole .b file. So too late. Right, so too late. Never mind. I will just read it to you. We're almost done with this lecture. So the backward Z is actually read in ASCII, exists, spelled out. And what it means is, okay, so to prove an existential, what do we have to do? Well, we have to demonstrate, we have to show that there is some particular n that this is true of. In other words, to demonstrate that 4 equals n plus n for some n, what we need is 2. So the tactic exists, says to Coq, the goal is an existential, and I am telling you what value you need for n in order for the body of the existential to be provable. And then, of course, the goal state is going to change to 4 equals 2 plus 2, which we can prove in ways that we've already seen. And then conversely, if we have an existential, how are we going to get juice out of it? Well, what juice would we get? we would get the witness. We would get the value of the n such that blah blah. So if we're given an existential assumption, we can use destruct on it to put into the context a variable n in this case, and an assumption that n has the required property. All right, so it breaks the existential into two and puts both parts in the context. Okay. Any questions about any of that? Very good. Then I propose that we break until 4:45. Break until 4:45, and basically what we've done is the first half of the logic.v chapter. So up to the place where it says programming with propositions. There are a whole pile of exercises to do with all of the things that we've discussed. They're mostly fairly small, and I think there aren't enough recommended ones, so I can't just tell you to do all the recommended ones and ignore the others. But see if you can get, in the next hour and 20 minutes, through the first half of that file, paying some attention to practicing with each of the connectives that we talked about. There will be coffee served. Maybe it's already out there, but otherwise in 10 minutes. This room will be open, and the 3 rooms upstairs will also be open. Okay, coffee is out front.